The second speaker we have is Dr. Saman A. Gorji from Deakin as well. Dr. Saman is a senior member of the IEEE, currently a senior lecturer of electrical and renewable energy engineering at Deakin. He has been actively contributing to Deakin's 7.5 megawatt renewable energy microgrid through various activities including research, real-world teaching in unit development. He is a recipient of International Hydrogen Research Fellow in 2023, a scheme initiated by the federal government of Australia and CSIRO for the UK and Germany. Prior to joining Deakin, he was a Foundation Research Fellow with the Center for Clean Energy Technologies and Practices as QUT, as well as the Future Energy Exports Cooperative Research Center. And he has contributed to a number of projects funded by Australian Renewable Energy Agency and Future Energy Exports in collaboration with energy sector stakeholders. Before that, Saman worked on an iMove CRC project as a postdoctoral research associate at Swinburne, where he received his doctorate in electrical engineering. His current research interests include modeling and design of power electronic circuits, renewable energy electrical systems, and microgrids for green hydrogen production. Dr. Saman, please.
Thank you, everyone, and thank you for the presentation. Sorry for the introduction. So, a slide before that. So, basically, I'm going to talk about the power electronics and green hydrogen and revolutionizing the green energy landscape at Deakin University. So, basically, I'm just trying to have a presentation in regards to what we have at Deakin University, particularly because we are going to host the Energy Summit in 2024 in Australia, and I would love to invite you all to join us next year. So that's why I'm just trying to make a link between my research and the infrastructures and facilities that we have on campus and in different campuses. My name is Saman, and Robert, my colleague, has contributed to this as well. So he couldn't make it today, but we are going to hopefully host you next year. Okay. I'm just mindful of the time, but at the same time, I'm just going to have the presentation quickly to be able to go through the video at the end about the microgrid and the facilities that we have. So basically, if you're going to talk about the supply chain of hydrogen and the power electronics, which my research is right now, we could just try to divide it in different sectors like generation of hydrogen, transportation, just the distribution, and of course consumption as well. I've seen a couple of posters yesterday in this regard that was really interesting, so congratulations to all the good students that are working in this regard at IITM. Just generally speaking, about Australia as a country that has some analogies, in particular with India. We're talking about the regional areas and the microgrids, the isolated microgrids that they have to be built because of the energy security. I've seen again some good presentations of your friends here yesterday. So because of this, there is a link in IEEE spectrum that says Australia is going all in on green hydrogen. And to be fair, it is true. There are massive investment in green hydrogen in Australia, simply because Australia, one of the main incomes of Australia is the export of coal, and based on the Paris Agreement by 2050, there will be no export of the coal. So Australia should be just looking for an alternative for the energy export to maintain their position in the market of the export of the energy. The other thing is, so basically federal and state governments in Australia are investing too much money on this one to make this transition feasible. And debates are existing as well about, okay, if you're going to go all green hydrogen, where are you going to get the water from? You will need the treated water. And this is, again, very fair argument and debate. So just in particular about power electronics, which is my research, if you just try to look at the problem, we can go through the system level research, the component level research and sub level research, that each of them would make room for improvement and exploration in power electronics. Grid compatibility and system integration. I was just talking with Professor Krishna about just the points about electrolyzer as a new loads, harmonics, and those kind of IEEE standards that are more based on different types of loads. Electrolyzer in particular is still a kind of unknown load at scale. Of course, we do have the equivalent load of the electrolyzer, but there is still much to learn about that. So grid compatibility, system integration, efficiency, cost, size, control, and reliability. So whoever works in power electronics would be familiar with these terminologies. And advanced control, digital twinning, and scalability would be partially having overlap with what Adnan has just presented. So just saying that it would be a kind of multidisciplinary approach. So this is where my story started as a postdoc when I was working at QUT, Queensland University of Technology. There was a big project funded by ARENA, Australian Renewable Energy Agency. Too many collaborators and industry partners. The intention was to build a 50 kilowatt microgrid, still a fair size, but the point was a hybrid technology. Two different types of battery, vanadium flow battery, and of course the lithium-ion battery. Different types of electrolyzer, anion exchange membrane, PEM, proton exchange membrane, and for the fuel cell as well. So this was a collective approach to say, if you're looking at an R&D problem to try to mix and match different technology, how would it work? Of course, it was not too easy, but again, appreciating that I've seen some kind of similar works with some students yesterday, and I was really impressed. So the idea of my project was a kind of started from a paper from our senior colleagues at the University of Adelaide, was on the proceeding of IEEE about DC is the future. So as a fan of DC myself, it's hard to be a fan of DC and a fan of Nikola Tesla at the same time, but I am. But Integral and Derek Abbott, so Derek Abbott, the editor-in-chief of IEEE Access, that is a good friend of ours as well. This paper was kind of an initiative for us to think about how could we improve the efficiency. I'm not going through the details, but of course the work was kind of, we could get a $1 million project from Australian governments in terms of cooperative incentive. And so then we were able to secure some fundings to be able to work on the power electronics research. So basically in this system, the takeaway was that fully DC microgrid, of course, we had to build in-house converters in power electronics system, but a lot of challenges, still a lot of work to be done, but the takeaway was the efficiency could be improved, and we did improve the efficiency. So this is going to be the note for me that I want to just say why we built Deakin Solar Farm. Deakin Solar Farm, this is on campus. I will run a video about this at the end, and you're more than welcome to visit it next year. So Deakin Solar Farm is basically a 7.5 megawatt solar farm with 2.5 megawatt, 1 megawatt hour batteries. And of course, the hydrogen aspects is going to be implemented. I'm not going to talk about this too much because we will have a very comprehensive video about this. Just all in all, this would give us a very good opportunity not only to contribute to net zero, to do R&D contributions in power electronics. So another type of work for us was, again, going back to the diagram that I showed at the beginning. So when we are going through the scalability, if we are able to show that, to demonstrate that it is scalable it is not just enough. We should work on the reliability and improving the efficiency, cost and size as well. So I was working on this one in particular. These are just in-house built prototype, like dual active bridge converter for this purpose, like a new type of converters. And these are just reconfigurable or fault-tolerant converters for the case that we have faults in power electronics. Again, I'm going to quickly cover this one, but again, another justification that Deakin University is building HICEL, a research manufacturing center for manufacturing the fuel cells. That would be the first one in Australia at the university level. So we are building this one again as a step towards manufacturing and workings on the reliability of the hydrogen equipment. And then there was another paper that I worked, and this was in particular about the challenges and opportunities in green hydrogen supply chain using meta-historic algorithm. This figure that I just got from my paper was, I'm just trying to highlight that we are talking about green hydrogen a lot, but we are sometimes kind of unintentionally neglecting the facts that are as room for improvement and room for just challenges and opportunities in green hydrogen. So if you think about the microgrid for green hydrogen production, I just highlighted, I'm not going through them. There are so many aspects for optimization. Again, when we're going to storage of hydrogen, compressed gas, liquid, or porous material, again, optimization. If you're going to have transportation, again, optimization based on the method and consumption as well. So this was actually kind of related to what we have at Deakin University. Battery Research and Innovation Hub, that is in particular about manufacturing of batteries, and Many Futures, it is on campus. We are hosting too many industry partners rather than we are just actually accommodating them on campus at the university. So for example, Carbon Revolution is a company that exists on campus, on a large campus of Deakin University that we have. It's just one example as a successful story of an industry that actually was initiated based on the university platform. So what I'm going to say is that next generation, as we are talking about the renewable energy and net zero goals, is the main reason that we exist. So basically, as a map of Australia, and Victoria in particular, if we say this is the Melbourne city centre, we have a battery hub in the eastern suburb. We have one campus here, one admin building in the city, two campuses here. This is where Adnan is located, the battery hub and the School of IT. This is Warm Ponds campus in Geelong, where I am located, and microgrid and Many Futures are there. The School of Architecture is just a few kilometers apart from us, and then we go to West Melbourne, that HICEL is located. What I'm saying, the idea of just kind of decentralized technologies in Victoria worked a lot for us. So at the end, I just want to, there is a 5-minute video. I just want to show that as the video of our microgrid facilities that was, if you can play this, and that's the end of my presentation.
Welcome to Deakin's Renewable Energy Microgrid. Deakin is dedicated to sustainable practices and research. That's why we're home to Australia's largest university-based renewable energy microgrid here at the Deakin Warm Ponds campus. Our microgrid is the centrepiece of Deakin's commitment to being carbon neutral by 2025. The microgrid covers 14.5 hectares. It includes a 7 megawatt solar farm, a 1 megawatt battery storage system, as well as a 1/4 megawatt rooftop solar generation on our existing campus buildings. The microgrid contributes significantly to Deakin's energy needs, supplying an estimated 54%, or approximately half, of the Warm Ponds campus's energy usage, while also reducing Deakin's carbon emissions by about 12,000 tonnes annually. Annual production of our microgrid is equivalent to approximately 3,000 Victorian homes. In addition to generating renewable power, it serves as a dynamic platform for research and teaching, offering invaluable insights into the future of energy. A microgrid is a localised group of electricity sources and demands or loads. It serves a defined location, in this case Deakin's Warn Ponds campus. A microgrid can be connected to the main power grid or autonomously as an island if needed in times of crisis, such as when we have storms, power outages, or for other reasons. A key element of the microgrid is the presence of a tool for managing the system known as a microgrid controller. This is a central brain of the system. It manages the power generation and demand within the microgrid to achieve the best usage and distribution. While a microgrid is a system characterised by distributed energy resources and a control mechanism, not all power systems qualify as microgrids. Microgrids may include diesel generators or natural gas turbines to provide additional power generation sources when required. Renewable energy microgrids use power generated from renewables. Greener, more sustainable way to generate and distribute power. Microgrids' resilience, efficiency and flexibility makes them integral to the future of energy.
Deakin's microgrid encompasses an extensive 7-megawatt solar farm, one of the primary sources of renewable energy on the Warn Ponds campus. This farm consists of approximately 22,000 solar panels, which are mounted on next-tracker systems. These follow the sun's path throughout the day, ensuring the maximum irradiation for the panels and improving their energy output. The solar farm is strategically located on a north-facing incline of up to 12% gradient, which in the southern hemisphere provides optimum solar production. The system has 34 combiner boxes that consolidates the generated solar energy. The combined energy is then transferred via larger cables to the main SMA inverters, which convert DC power to AC. The main SMA inverter, each having a capacity of 2.5 MW, carry out this critical transformation process. In addition, the solar farm includes 4 different 60 kW research arrays, each possessing unique characteristics. They include arrays with normal panels with and without trackers, frameless panels, and bifacial panels offering rich research opportunities in solar photovoltaic technology.
The control room is the central hub for managing the microgrid's operations. While the specifics are complex, it's worth noting a few key components. The human-machine interface workstation allows for the operation of switchboard circuit breakers and provides system status and performance data by the supervisory control and data acquisition system. This SCADA system plays a crucial role in monitoring, coordinating and controlling the various components of the solar farm and the battery. In the event of a blackout, the control room is backed up by a UPS battery, ensuring that critical equipment remains operational and the microgrid can be monitored remotely. The high voltage connection is vital to the microgrid and allows for the efficient transfer of electricity generated by the solar array to Deakin's electrical network. It's equipped with protective elements like power quality monitoring and circuit breakers and is the interface point between Deakin electrical network and the electricity grid. Here at Deakin, we're helping to connect industry with research, training and commercialisation opportunities. The microgrid is a valuable and accessible reference point that can support and demonstrate the increasingly important role that microgrids will play as distributed energy resources for rural and remote locations.
The Deakin microgrid is a unique on-campus facility for research and training. It can be used as a living laboratory, using data retrieved live to identify microgrid innovations. It has a digital twin, and combined with our power system engineers, the School of IT, the Faculty of Science, Engineering and Built Environment and Deakin Energy Networks, it can help connect industry with research, training and commercialisation opportunities.
Yeah, thank you very much,